We're just going to be going over some of the principles of the lab that we just did, and this is lab 4, which is the ladder logic. So ladder logic is used to program which of the following devices. Well, it's not going to be microcomputers or microchips or microcontrollers. Those all sound very similar, and we can X them all out. Not x86 processors, we dealt with that in a previous lab, nor Raspberry Pis. It's going to be a PLC, which is a programmable logic controller. Next, we are going to look at this diagram. So it's asking us, M1 in the diagram is which of the following? And well, M1, if we remember from the lab, is this part right here. And it's not a switch or a controlled resistance or a gate. It's also not a closed or open contact, right? The switch itself is going to be this part right here. It's going to be a relay because it's going to relay whatever signal we have here, because currently with it open, there's no signal. Once this closes, there is a signal, and it's going to relay it to the actual NC, which is normally closed, or NO, which is normally open switch for our ladder logic. And now we're going to look at the NCs and NOs here. So we're asked to define what logic gate this would be. Well, if we look at this, we know that, let's do a truth table. So these are both closed circuits right here, right? They're normally closed. So that means the current is going to flow through both of them. So when our switch is open, these are closed, meaning that when our switch is 0, 0, our output's going to be 1. So when 1 is open, when we have like 0, 1, our output is still 1 because current can still flow like this way or like this. And the same thing if we have 1, 0. But if both switches are open, current can't flow through. So if we have a 1, 1, our output is 0. So we are going to have 1, 1, 1, 0. And that looks like a opposite of an AND gate. So this would be a NAND gate. We are to define what logic gate this would be. And well, it's very similar to what we have here, just with normally open circuits. So normally open, no current is going to flow through here, right? So when we have 0, 0, it's going to be an output of 0. But if we just close one of these, or if we can close both of them, the current can flow through whichever one is closed, or both, if they're both closed. So then we would have 1, 1, 1 for our outputs, which means this is going to be an OR gate. We're going to define what the logic gate would be for this. And well, if we have two of these are normally closed, and the switches are both open, so we're going to have 0, 0 inputs. Well, our output's going to be 1, right? Because the current can just flow through here. If we open just one of these, or if we open both of these, no current is going to flow through here. And if we do that, it's going to look like this, a normally open. And so our output is going to be like a 1, 0, 0, 0. And this is the opposite of an OR gate, so an OR gate, and so that is a NOR gate. Next, we're going to define what logic this one would be. Well, with this one, we can see is very similar to this one. If we have these two, which are normally open, we need to close both of them because they're in series with each other to get this light bulb to light up. So to close both of them, we are only going to have our output be high if both our switch inputs are high. Otherwise, it's going to be low. And this is a AND gate. We have the switches in the diagram are what? Now, this previous one was asking us for the logic gates. This one is asking us for the switches. So not what type this is, but the switches. This is going to be either an NO or an NC, normally open or normally closed. We can see that it's open right here, so it will be normally open. The switches in this diagram are what? Well, we can see they're closed here. And so are they normally open or are they normally closed? They're going to be normally closed because they are both closed here. And that's all for the review of this lab, and those are the key takeaways for what we needed to have learned.